So, in assembly language, really, we're just kind of at the machine code level. Our assembly language is translated directly into a machine. Every line of assembly language corresponds to an instruction. And all higher level languages ultimately become assembly language or equivalently machine code, right? So, but in program in C or C++, typically a line of C code becomes multiple lines of assembly. So you can do some, in C you can have a long mathematical expression, A plus B times 10 divided by B. That corresponds to multiple assembly language instructions. You've got add, subtract, and compare, as well as multiply. There's actually an unsigned divide and a signed divide, both of those. The compare instruction subtracts two numbers, but it doesn't store the result. It just sets the corresponding flags and status register. The carry, the overflow, the negative, and then a 0 flag. And then based on the compare, then if you look at the branch instruction, the B instruction in your book, there's like 20 different variants on that. Branch if equal, that means if the 0 flag is set. So, and that's how all this is, all of your if statements and things like that in C are implemented at the machine code level. You compare, if A is equal to B, the way that becomes, what that becomes in assembly language is you can compare A and B. If that sets the 0 flag, then they're equal. And then you branch and do one section of code when they're equal, branch to another section of code when they're not equal. So there are variants of these, again, add S, sub S to set the flags, or condition code bits. There aren't different add operations for signed and unsigned numbers. Again, there are variants on all these. You can add 8-bit values, 16-bit values, or 32-bit values. So, add B adds the corresponding, does a byte addition. But there aren't variants for signed and unsigned. It's the same add instruction. Actually, with 2's complement arithmetic, you do the same operation with signed and unsigned. But what happens on overflow is different if the 2 values are unsigned versus signed. The C bit, or the carry bit, I think in your book you refers to it as an unsigned carry bit, is set on an unsigned operation overflow. Typically, in programming C, you just use 32 bits variables for everything. Even, if you know the value is never going to be greater than 100, it's just a lot more. Instead of using a char or an unsigned char, we don't really care that much about memory these days. It's cheap, it's plentiful. So typically you just do ints for everything, right? Well, in programming, what we're doing in microcontroller level is a little bit different because sometimes we're dealing with 8-bit data coming in, and as opposed to 32 bits from some sort of sensor. So often we'll be forced to do 8-bit 8-bit arithmetic or 16-bit arithmetic or 32-bit arithmetic. But say you're adding two numbers, say it's 255 and 100. Well, that's going to overflow. If you're treating those both as unsigned, 255 plus 100 would be an overflow, doing 8-bit arithmetic, right? That would set the C bit, okay? So you could do an addition if you know the two numbers are unsigned, you've got to keep track of that. You add 255 and 100, that will set the C bit. Okay. You could then check to see if do a branch if the C bit is set and take appropriate action, whatever that is. Okay. On the other hand, the B bit, which is the signed overflow bit, is set on signed overflow. So you take that same number as a byte, the 255, which is as a byte, that's FF. If that's a signed number, it's -1, right? -1 plus 100 is not an overflow. Okay. So if you do that operation, it would set the C bit, but it would not set the B bit. And then you, as the programmer, know whether those two numbers are signed or unsigned. And so you would have to check the corresponding bit to take appropriate action. Okay. Now, on the other hand, if they were plus 100 and plus 100, that's going to overflow on signed arithmetic, right? Because signed arithmetic, you just have between -128 plus 127. So if you add 100 and 100, what that will do is set the B bit, but not the C bit. Because 100 plus 100 is 200, and that it doesn't overflow 8-bit unsigned. So again, you have to keep track of what your values are, whether they're signed or unsigned. There's no predefined data types for you like you have in a lot of higher level languages. So what I wanted to do now is everyone got Code Composer Studio up. We'll go through the process of creating a new project in assembly language. I've got a new main program that illustrates how to use variables in memory. Okay, and then we'll run through some examples in the book after I talk about what this does. I didn't really get enough time last time to go through that assembly language example in detail. Hopefully, were there any questions on the homework? You had some programming assignments in there. The homework is due today, right? Any issues there? I know some of you still having some trouble getting things to any word yet, Andrew. So, does anyone have any tips for the class? Anything you ran into that you had to find a workaround for? Any issues? Okay, so is this up? So I'm going to create a new CCS project. We'll create this from scratch. And then one issue Andrew was having, he had not let his Code Composer Studio do the update, so he was using an old version of the compiler. Okay. We don't know yet whether that was actually the issue he's having or whether he's got a bad board. His code was correct, but it wasn't running, and it would run on my board, but wouldn't run on his board. Okay. So the latest version of the available compiler here is the TI compiler 20.2.2. So make sure you have that version. If not, you want to actually go to the help menu and do an update, okay? And then it will update automatically to that version. There's actually a version of the GNU compiler in here, but we're not using that. Again, the assembly language syntax is a little different. He doesn't even talk about that in the textbook. So he does talk about the TI compiler, so I chose to use that one for this course. Call it, I don't know, assembly with variables or something. And then we're just going to create an empty project without even a main. And then on the course website, so open up a browser. Go to 354 Lectures, and then lecture 10. There's a new main.s. So right click and save link as, and then you want to save this in that same folder you just created. So it's in your workspace, assembly with variables, and then save it there. And then now it popped up here. Do I need to go through that again? Starting where? Starting from downloading the file or creating a new project? I can't hear you. Someone said I needed to do something again, but I can't hear what that was. Okay. So get to the course webpage. Is that okay? And then lectures. And then under today's lecture, there's a main.s. Okay. Right click, save link as. And then you have to know where your workspace is, your Code Composer Studio workspace. I mean, I think by default, is it under like your username workspace? That's where it is here. Okay, but you can actually change wherever your workspace is as well. So under your workspace folder, you have folders for every corresponding project you've created in Code Composer Studio. Now, in Code Composer Studio, you can delete old projects, and that's fine. You know, it won't actually delete these files unless there's a little checkbox. So normally I go ahead and click that checkbox to delete the stuff, but you don't have to. But if you've got old folders here that aren't appearing as projects, you could go ahead and delete them. Now there's some here system projects like this DVT, remote system temp files, metadata, was it JX browser data? Don't delete those. Those are created by Code Composer Studio. But the others in this 354 source one, and then so go to the folder that we just created and then save the main.s there. So the other thing that we have to do, our main.s uses the simple I/O routines to print to the serial terminal. That's, you know, instead of using the debugger to step through this, we've got a simple way to actually print stuff to the serial terminal. So we need to add those files to the project. So right-click on the project, and then select Add Files. And then again, you have to browse to your workspace. And then these are the files that we downloaded last time. I haven't done any updates yet. Okay. And then you can just select them all. Or add them in one at a time if you want. But, okay. And then again, what I'm suggesting is we link to the files so that if they are updated, they'll automatically be updated in the project directory. They're not copied here. And then allow it to update the headers. So let's take a look at this main.s. It's a little different than what I had last time. Is this the right one? Yeah. this is not the right one. Okay, so actually let me fix that. Hang on just a minute, sorry. I must have copied over the wrong file. So let me log in my desktop. Okay, that's the right one. Okay. That's where it messed up. Yep. Okay, so let me update this page. Okay, this is the right one. So it's on that. So you may need to update your web browser, but go back here and re-download this file. So save link as, and then you want to save it in the same directory. Now notice it changes, tries to change the name because you've already got one, but click on the main.s that's there because you actually want to, you should get this warning, yes, I want to replace the one that's there because it's wrong. And so here's, and this gets a little complicated again, because the variable storage, which I'm not going to talk about at this point, but there's actually 2 steps to storing variables in RAM. And these would correspond to actually global variables in C or static local. We'll talk about variables that you define inside a function that are local, but they aren't really named. They're stored on the stack. So we'll talk about how to use the stack next time. But this would correspond to variables that always retain their value during the lifetime of your program. So they would be defined outside of a function. So generally, you don't use these very often. Often in computer science, they tell you avoid the use of global variables, right? So these are kind of the easiest variables to use at this point for us. So we have this data section, which tells the linker to set aside space and RAM for us. And then here is where we're defining the name of this variable. I call it var x. You can call it anything. And then it's setting aside 32-bit space, 4 bytes, and storing 100 there. Okay, so the little comment tells you that. So for other variables, Z, Fred, just repeat those 2 lines. But the other thing that you have to do in the text section is then define a pointer to that memory location. This pointer is actually going to be defined in, here it is, in the text section, which is your flash ROM. Okay, you can't write to flash ROM, you can only read from it. That's where your program is stored. We can write to the data section, which corresponds to RAM, but we can't write to this text section. But we can tell the assembler to figure out what the address of var x is and store the address there. So the convention I use, I follow what he does in the book. I call this pointer to var x. So the assembler is going to fill this in for me. when we assemble and link the program, it knows where it's going to store this var x. You know, it's going to be in RAM somewhere. The assembler will say, take that address and put it in this location in your flash ROM. So loading using a variable is a two-step process. First, you have to load the address of the variable. And then, remember, this is the indirect addressing. So we load the address into R5. That address won't change. That's always, that's in flash ROM. Whatever that address is, we load it into R5. Then this is indirect addressing. Go to that address and load that value into R4. Remember, I initialized varx to 100. Now to print it, I have to move it into R0, because print int just prints whatever's in R0. So I loaded them into R4 and R5, so I don't have to worry about them actually being wiped out by any of these function calls. Remember, the function calls can wipe out R0 through R3. So print it. So we should see 100. I increment that by 1, add 1 to the value, and write it back to memory. R5 still has that location. So now I store that back into RAM, okay, instead of using, before we just kept our variables in registers. But here's how you would actually read and write a variable from RAM. The strings are a little bit different. The strings are actually stored in flash ROM. And so the string addresses, we actually have to use ADR instead of LDR to get those. You can also, of course, store char arrays in RAM if you wanted to change these, but these are actually string constants. You'll get an error if you actually tried to write to these, because these are actually stored in flash ROM. Okay, so that's basically it. We're going to go through this first exercise together and then see. So here's some just examples he's got in his book. So we'll try to duplicate the code he has. So 118 of your book. Got example 3.6. Now there's some slight differences in what he does than what we have, but we'll try to keep it together as much as we can. Now what I'm going to do here too, let's see, I guess a couple things, you know, you can either do a debug or a release version. The release version should actually be smaller, but of course you can't run the debugger with it. Okay. But let me switch over to the release version and then make sure it actually builds without errors. So you should be able to run this.
Would you say the page that was on?
118. I'm going to bring up now it's running some other program here. I haven't actually loaded the new program, but now if I flash the program onto the board. So I left some of the same stuff that was in here last time. I think it's still. Okay, and what the program did, actually, you can see it printed 100 but it tacked it on to whatever was on my terminal before. I didn't, you know, if I reset my terminal, reset terminal, reset my board, it starts out, it prints the value that was stored in memory, prints that string. Again, we've got this bug we consistently have to work around. And then notice it incremented. So it did this in a loop, it incremented the value, stored that back in memory, and then at the beginning of the loop, we reread it every time. Okay, and then it's 102. So let's actually now, for this, let's copy this and then paste it and call it example 0306. Call it whatever you want. Now, in his examples and his book, he never prints out any of these variables. Okay, so because I guess he expects you to step through this with the debugger, but we've got this simple way to display variables. But in this first example, he's dealing only with the variables n and m. So we'll make the corresponding changes to our program. His first example here reads variable n, multiplies by 5. So instead of Rx here, I'm going to change that to capital N. We could give it an initial variable and then write something to that location, or we'll just initialize it so our code will be as much like his as possible. I'm going to initialize it to 10. Okay. Pick some other number if you want. Now, I'm just going to duplicate these two lines because we need another variable. We need a variable m. And we don't actually read from m, we just store there. So I'll just set it to 0 because we won't actually use that location. So now we've got the two variables. We have to do the corresponding pointers. We have a pointer to m, and then we're going to force the compiler to store the address of our variable in RAM at that location. And again, duplicate this, have a pointer to n, and make sure you change the corresponding variable name so the linker will fill that in for us. Okay. Now, I'm going to go ahead and get rid of all this string stuff because we're not using it in this program. I'm going to go ahead and leave the stuff here that's incrementing the watchdog timer. Actually, we're not going to have anything inside our while loop either. We're just going to have our microcontroller run this code once. So I'm going to delete everything that's inside the while loop and just leave that. This is an infinite loop in assembly. I've got a label, then it branches right back to that label. Now I do need to initialize, call the output init routine, because that initializes the board to do serial output. Now the rest of this is going to be fairly similar. Load R3, comma, actually I like to tab things out, R3, comma. Now we have to use pointer n, where he's got equal n. Remember, he's using a different assembler, and this is about the only difference between the two. Where he uses equal n, that assembler uses that notation to load a pointer. Ours has to do it differently. and then load R1 from that location. So what I initialized it to 10, I think, right? And then the rest of this is, so the algorithm here is read variable n, multiply by 5, add 25. So we've read the variable n. I'm going to move it to, actually move the constant 5 into R0, and then multiply R1 So any questions at this point? This multiplied with the 3 operand, multiplies the last 2 and stores it in the leftmost. So at this point, I've read n into R1, 2-step process, load the address, load the value, and then I move 5 into R0. So now that I can multiply 5 times n, and I'm storing that result in R1. Again, you have to work at a really low level here when you're doing everything in assembly. So multiply by, no, add 25, I guess was the next step. So again, I've got to get that value into, let's see, put that in R0 and move 25 immediate. This is the decimal, and then add R0 and R1 and store the result in R1. And then now we're going to actually load into R2 the address of M. So where he has, did I call PTRN or just PTN? PTN. So up here it's PTN, not PT, and PTM. And then we're going to store that result back in that location. Now, and that's the end of his code. We should have stored in M 25 plus 5 times n, but I'm actually going to call print int to make sure we've got that. I've got the value, I've got m stored in R0, right? So I don't need to reload it. It's already in R0. So I've stored it in memory. I'm just going to call print int, and then I'll call print new line. Now, because this is just outside my while loop, it's just going to be executed once. If we moved it inside our while loop, it would be executed millions of times, but we never changed the value of n, so you just see the same number displayed over and over. So here's where cross your fingers, click the hammer, call the hammer, and it failed. Did it fail? Maybe it didn't fail, it failed. Illegal mnemonic. Oh, why do I keep doing that? You guys keep letting me do that. I'm testing you and you are failing miserably. It's not a call, it's BL, right? For branch. So the BL is essentially a function call, right? And then And 5 minutes later on this machine, it actually transfers it to the microcontroller board. So what we should get, I put 10 in there, adds, multiplies by 5, adds 25. So what we should see is 75 when this thing runs. And that's what I see. Again, it's appended to the previous output, and it only runs once because it's not in the while loop, but every time I reset my board, you reset the board by pushing the little button that's on where your USB connector is. And then every time I reset the board, I get 75. So I'm going to give you guys, okay, you guys, I'm going to come around and help. I want you guys to do the example on the next page, where convert a variable n ranging from 0 to 1023 into a variable m, which ranges from 0 to 3000. So it essentially multiplies m by 2.93255. We're not using the floating point processor. So he does that by actually multiplying by 3000 and dividing by 1023. So he's got 3 variations of this example program. So do the top one, see if you can get that. And it's not much different than what we've got, but initialize n to something, and then verify that you get the right result. Okay, print it out. You can try, the first block. The second block, he does, what's he do? Well, he does rounding. Shows you how to do rounding. And then the third block is actually does, instead of doing multiplication, he does shifting. So work on that. You've got about 10 minutes. Is anyone having trouble?
Hey, can you just scroll up to the top?
Where the variables were defined, or?
Yeah, that board and all that. So that's how you declare n.
Yeah, this is declaring n, the variable n, in memory, in RAM. Okay, it's in a different section than my code. So this all goes into one file, that executable file, but when you load it into the microcontroller, it's only this section of code that gets loaded into the flash ROM. It actually, the loader actually initializes RAM to 10 here every time you run the program. So, but that's handled automatically. That's because you have a main.c also. So when you go to create a new project, what I did was I created an empty project, not one with main C. So since you have a main.c, it actually used that instead of main.s. You've got main.s here. Okay, now there's still warnings here. So you should have it's saying it's not there. Okay. It's a workspace. Okay, well, it can't go there. It has to go wherever your workspace is for this. I think that's in. Same workspace version 10. Okay. So let's see if you go shortcut somewhere. See anything that's ABC. Users. Same. Space version 10. And so this is where all of these projects are built. So you need to remember this. And this is the assembly. And then you have to save it in that directory. And then there it's there now. Now I think you may have issues with these others as well, depending on where the URC and URH, because they didn't look like they were.
Yeah. This is not the program.
Oh, let's not refresh your browser after this is assembly variables. Yeah, that's the right one. This is here. And last time, I need to save this as. So what I suggested you do is create an EE354 source directory. Save it there. Save that there. So not the right versions. Delete. And file. Not here. You actually get
Friend.
Yeah, if you can I don't know.
You say friend? Is it? It is 0.
You're right, though.
And so now you'll start with assembly, you'll just duplicate, copy and paste this project.
Okay. This is blocks.
paper.
Oh,
You don't have the latest version of compiler either. Yeah, but it needs to do an update. Now, it's here. Check for updates. Allow us to update everything. So this will take a little while. Well, actually, I have to go back through that process again to recreate the project. Sure. Oops, sorry. So I'm not seeing it here. I'm not seeing it here in this. Okay, so I don't know. So we need to actually download it to.
These are accomplished sets.
So your workspace is.
Yeah, these are the
Oh, does that work?
So your desktop.
my place been being weird. Let's go. Yeah.
Here.
I was not
Sure,
sure.
that's the right.
That's it's already set for this nice. I just flash it.
So it has to actually, what's the name of this particular project?
For whatever reason, no, I don't listen to it, like, on this thing, and that, because for some reason,
See it on there.
this is.
Oh, you must have saved it on one above.
I saved one on, but it's supposed to be like, oh, yeah.
Yeah.
It's not.
Yeah, it needs to go, each project has its own file, so it's here now. Do you have the simple IO and the UART routines? Did you download those last time? Okay. So the other thing you need is these three. Well, since we're going to be using these over and over again, what I suggested everyone do is create a EE354 source folder, and then put these in here. And then if we update these,
Yeah.
then you can just change them in this folder and they'll automatically be updated in all of your projects. But now back in Code Composer Studio, we actually have to add these new files. Since I didn't put them in the folder, but they're here and here. I'm going to select them all. Control A. And then I'm going to link to them instead of copy. And now, and you can do the debug version, the release version. Should theoretically do this. So now it's building. You should get that means our time together is up, but I actually don't have class for another couple hours, so anyone still needs help and you don't have a class right now, I'm willing to help. So or you can catch me up in my office in an hour. I'll be free from 2 to 3. Everyone else okay? Yes, no, yes. That sounds actually like a odd rate error that your serial terminal is not set up correctly. Are you using the terminal that's built into the it doesn't, yeah, click on the settings. Oh yeah, baud rate is 115. Yeah, it was sending data at one speed, but your terminal was thinking it was sending data at much lower speed, and that usually causes it to read the ASCII data incorrectly. Probably. Yeah, I was kind of surprised that it was a pilot next to it, but I didn't really look at the serial comments. There's too many things that can go wrong. Eventually, I see them all.